Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our lesson on partial derivatives. So we've done, in the last video, we've introduced how to differentiate um, a function with two variables, right? And so the first thing we have to do is make one of them constant, and then we differentiate the variable that's not constant. And so we do this twice. So that's how we solve partial derivative equations. Okay, so here we've done example one. We've also done a bit of examples from my homework. This was in the previous video. Um, so today we're going to do more examples. And yeah, let's just hop right into it. So for number two, or our number two exam, our second example in the textbook. Okay, let me do example two. Here we're being asked to find partial derivatives. So here we're saying if my partial derivative fxy is equal to sine of x over 1 plus y, I have to calculate. So I have to calculate my partial derivative with respect to x, as well as with respect to y. Okay. Okay. So what happens here? Well, first I do this with respect to x. So here this is the same as this notation. We do f sub x. So what does that mean? Well, our y will be a number. Our y will be some fixed number. Okay? So again, we just take the derivative like normal. So I do a chain rule here. So derivative of this. Okay, let me just let's do this. That way I know I'm taking the derivative. Here I get the cosine plus whatever is inside. And I chain rule. So I take the derivative of this thing, right? And so what is this? Let me rewrite it because I don't want to do a quotient rule. So we take the derivative of this thing using a product rule, right? So how would this look like? Well, the first term, we take its derivative times x. We add it to the first term again, and then we take the derivative of my other thing, right? So it's like the derivative of my first thing times the second thing plus my first thing times the derivative of my second thing. Okay, let's take the derivative of this one. Actually, it's my fault again. Maybe I shouldn't have done this because I would still have to do quotient rule. Bro, I've done this. This is my second time doing this in this video. Let me let me stop doing it for once. Okay, there. Let me just do a quotient rule. And we did talk about it in my previous video, so I'm not gonna explain anymore. But this is, so we take the derivative of this thing, right? So this low d high minus high d low over low squared. So this is my mnemonic for quotient rule, low d high minus high d low over low squared. I did explain this in the previous video, but basically high and low mean numerator and denominator. I just used high and low just to make it catchy. Okay, so we take the derivative of this. here in this case, x is a variable. So this becomes 1, right? Here, well, y is a number. So this becomes 0. And so I actually just have 1 plus y over 1 plus y squared. And you know what? I'm just going to simplify. Doesn't matter. I just have 1 over 1 plus y, right? So I just simplified that whole thing. And so, well, now I have my answer. This is just cosine of x over 1 plus y times 1 over 1 plus y. And we're done. Right? Okay, I got that one. Now we do my partial derivative with respect to y. So this is when I make my x constant this time, right? So again, I do the same thing. I take the derivative of my original two-variable function. I see it's a cosine. I do a chain rule here. Okay, maybe I shouldn't have erased what I previously did. Then I do a quotient rule. So low d high minus high minus high d low over low squared. Okay, now here my x is a number. So this means this is 0. My y is a variable. This is 1. This is 0, so this is 1. And so I have negative x over this. So this is just 0 minus x. So it's just minus x over 1 plus y squared. Okay, next time when I'm taking derivatives and I'm doing that, I'm not going to erase it. So here we have cosine of x over 1 plus y times negative of 1 plus y squared. And we're done. Nice. Okay. Let's move on to how do we interpret partial derivatives? Right? So while we were solving this, we could solve it, right? In calculus 1, a derivative is a slope. But what about partial derivatives? What is that? So let me just read what the textbook is saying. To give a geometric interpretation of partial derivatives, we recall that the equation z equals f of x, y represents a surface, right? So here we say that my function of two variables with the output z, it doesn't represent a plane curve like how y equals f of x does, but instead it represents a surface. Let's just call it S. So it represents some surface, a quadric surface to be specific. And that's the graph of f, right? What are other interpretations? Now, if, let's say our f, a, b, we're saying a, b is a point, and this is equal to c, then what does that mean? Then our point, let's call it P, which has coordinates A, B, and C, is on the plane. Or not necessarily on the plane, on the surface, because it could be a plane, could be a sphere, it could be a hyperboloid, a paraboloid, an ellipsoid, ellipsoid, an ellipsoid, and yada yada yada. So just some different quadric surfaces. Um, yeah, it lies on that surface S, right? What else could we say? If we fix y equals b, let's say y is a constant b, we are restricting our attention to some curve in which the vertical plane y equals b intersects S, right? And so in other words, um, that curve, if we restrict it with the vertical plane y equals b, is the trace of S. So we're actually intersecting a plane with a, and this is not new. The idea is that, so here's the idea. If we have y equals b, and where b is some fixed number that we don't know, and let's say we have some surface S. Let's say this is in the XYZ plane, XYZ 3D space. Y equals b would probably look, let's say this was b, right? We probably have a plane like that, right? And we see here, oh, intersects this. Well, this is what we call the curve of intersection. The intersection curve. I don't know what you want to call it, but it's that trace of S in the plane y equals b. Because we have two quadric surfaces that intersect together, right? Okay. And likewise, if we have a vertical plane x equals a, so it's just the other way around, then it intersects S again, our surface S. And both of the curves pass through the point P. So let me just show what that means, just to be specific, or just to have a geometric idea. Okay, so there's the picture. It's all the way over here. But yes, if we make our y fixed, y equals b, then we have a plane that intersects this curve right here in this blue line. And same goes when we have an x equals a, if we have a fixed plane. I don't know how long this is, something like that maybe. Then it would intersect there. So those blue lines are the intersection curves, right? And we're saying that they both pass through the point P, right? Because they pass through this point P. Now, what else can we say about it? Let's note that C1. So here we're referring to C1, this one, if you guys can't see. C2 is this other intersection curve when x equals a is fixed. So when we're referring to curve C1, C sub 1, that's the graph of the function g of x equals f of x b, right? So we're saying that, what do we say? So here's where our partial derivatives come in, right? Actually, let's summarize what we just did. So if y equals b, then curve C1 is the intersection. I'm just trying to write it in my own words. Of vertical plane. We're gonna call it y equals b. And our surface, which we'll call it S. And if x equals a, then curve C2 is the intersection of that vertical plane, x equals a, and surface S. And both of these curves, so we're going to say both C1 and C2 pass through our point P with coordinates A, B, C, right? So those are the three things or three observations we can deduce from this visual, from this geometric visual, right? What else? So now here comes partial derivatives. We're saying that C1 has the function, let's just call it, I don't know, g of x is equal to f of x, comma b. Why do we say that? Here we make our y fixed. And so we were able to create this curve C1. And so that curve C1, has a function of a single variable, g of x. C2, on the other hand, oh wait, there's also something we have to say about its slope, right? Now we actually have a slope. So we not only have this curve, we have a tangent line, T1. Now we're looking at this red line here. So at a particular point in that curve C1, we have a slope, right? Here we're saying that it has that function, and it also has a slope. And slope of, we're going to say, tangent T1 at our point P, is just its derivative, g prime of a, which is equal to f. We do f prime, does that make sense? No, we don't do f prime. We just do f sub x, ab, right? Our b is fixed. We replace x with a here. So that's our partial derivative, right? So that's what we're trying to say. And similarly, C2, on the other hand, also has a function. Do we just call it like what? In the textbook, they called it g of y, capital G. So I guess that's fine. And this is equal to f of a, comma y. Here we make x a fixed number a. And then again, it also has a slope of tangent. And we call it T2. And I think it was this one. We're talking about this guy over here. We have curve C2, and at a particular point P, we determine the slope of that tangent line. And we're saying, so at P is the derivative g prime of, here we say b, is equal to f sub y of ab. So here, well, now we're getting the partial derivative of that curve. So that's the only difference. At the end of the day, it's still a derivative. We're getting the slope at a particular point in our curve, but this time we're considering a 3D version. So we now have more coordinates to work with, because initially we had two, and now we have more coordinates to work with, right? Because if we're only taking the derivative, that's only for plane curves, right? If we were, let's say, in the xy plane, and we took the derivative of the curve at this particular point, so we get a tangent over there. We take the derivative at this point. But if we were to have a 3D version, and we have a surface, right? We have some surface. And if we have some tangent, well, now we're looking at a couple of derivatives we could find. And so we not only get this, okay, let me do a different color. We not only get this derivative, the derivative of this, or the slope of this line, but we also try to get the derivative or slope of this line. And so that's how we were able to do partial derivatives, because we need to take into account all of the derivatives in that particular point in the surface. So that's the idea. That's the geometric interpretation of partial derivatives, right? So to summarize, that was a good ending by the book, by the way, or the closing of the book. They said that partial derivatives f sub x of ab and f sub y ab are slopes. So we have two slopes that we're looking for because we have two tangent lines. And there are two tangent lines specifically at our point P. Right? Do the traces C1 and C2 of surface S in the planes y equals B, x equals A. We don't have to write all of that, but that's the idea, right? Okay. Let's do one more example. And then we'll we'll call it a day because it's also nighttime here. Okay, let's do one more example and then we're done. Okay. Here we're given a function of two variables, f of xy is equal to 4 minus x squared minus 2y squared. And we're being asked to find f sub x, 1, 1, and f sub y, 1, 1. So we're trying to find the two slopes of two tangent lines at this particular point, 1, 1. Right? Okay. And interpret these numbers. So the numbers that we get, we interpret them as slopes. All right, let's start. So first we have to take the partial derivative at f sub x, right? So let's do that. So here we take the partial derivative of f with respect to x. So here we make our y constant. Let's make our y constant. So again, we take the derivative of this thing, right? Since y is a number, this becomes 0. This becomes 2x. This becomes 0. So we actually just have negative 2x, right? And now let's try to plug in our f sub x. So we plug in my number here. For x, we plug in the 1. We get negative 2. So that's one of them. And then we do the same thing. Now we do it with respect to y. So this time we make our x a number. So again, we take the derivative. This is a 0 because it's a constant. This is a 0 because it's a constant, right? This one, on the other hand, we multiply by 2, we get negative 4y. And so if we get f sub y of that same point, we multiply 1, we get negative 4. And so the slope of one of my tangent lines is negative 2 and the other is negative 4. Right? Yeah. And so this is actually a paraboloid. How do I know? This is a surface, right? We can rewrite this as z equals 4 minus x squared minus 2y squared. If I take out my z, so is this taking out again to identify what surface it is? Well, here I get x squared plus y squared equals 4. And so at my xy plane, I actually get an ellipse. If I take out my y, well, I get a parabola. And if I take out my x, I get a parabola as well. So to be specific, it's an elliptic paraboloid. So that graph is a paraboloid. The vertical plane y equals 1 intersects it in the parabola z equals 2 minus x squared, y equals 1. And as in the preceding discussion, we label it C1. The slope of the tangent line, this parabola, is the point 1, 1, 1. Is f sub x 1, 1 is negative 2. And we notice that the tangent line slopes downward in the positive x direction. And similarly, the curve C2, in which the plane x equals 1 intersects the paraboloid, is the parabola z equals 3 minus 2y squared x equals 1. And the slope of the tangent line at 1, 1, 1 is f sub y 1, 1 equals negative 4. So what in the world did I just say? So let me just take a screenshot of that picture. But all I'm saying, okay. So here's the paraboloid. Okay, wait, let me just take a screenshot. Here's the parabol. Why did that go there? Here's the paraboloid, right? Here's our 3D space. Here's the point 1, 1, 1. Here's the point 1, 1. We took its partial derivative with respect to x and y. So this is with respect to x. And then this is with respect to y. How do I know? Well, I see y equals 1 and x equals 1 here. So I know this one's a fixed y, this one's a fixed x. Fixed y, fixed x. right? And here we see that curve, right? That curve. Okay. You can see it. It's the blue curves. And then we have this red line or red lines. One's for f sub x, one's for f sub y, right? Yeah, and that's basically the oh, why did I do that? That's basically the idea of partial derivatives. We're getting two slopes, or at least in this example, we're getting two slopes because we have two tangent lines that we could solve for given a quadric surface. And we definitely can't do that with a derivative alone. You have to do it with respect to x as well as with respect to y. Okay, that's all for this video. I hope you guys enjoyed. I will do more exercises on partial derivatives tomorrow. And yeah, I'll see you all in the next one.